Hi, everybody, and welcome to week 5 in astronomy. Well, this week we're going to have two really important topics. We're going to finish up talking about history, and then we're going to get into telescopes. Last week we started history, and we talked about Aristotle, and we talked about that geocentric, heliocentric model and that competition kind of which model was going to win. We got into Tycho Brahe, wacky old Tycho Brahe, Johannes Kepler, and of course Copernicus. Copernicus with his heliocentric model that, oh my goodness, the Earth actually does go around the sun. What a crazy idea. But Copernicus died shortly after his ideas were published. So he wasn't around to take the heat. He wasn't around to actually pick up that ball and run with it. He wasn't around to actually fight for his ideas. The guy that actually took that idea forward was Galileo Galilei. And if you talk to anybody in the history of science and said, who are two of the biggest names in all of scientific history? Well, Galileo and Sir Isaac Newton are near the top of that list because they are really, really important. So Galileo Galilei published some books about the history, about astronomy and about forces in motion. And he had the audacity to say that the Earth actually went around the sun. Well, he got in trouble, big trouble. He got put on trial. He was threatened with torture for actually saying crazy things. Other people had been burned at the stake. We're talking the Inquisition long ago and far away for saying nutty things like the Earth actually orbited the sun. And so it's a wild and crazy story, but we're going to talk about Galileo. Then a generation after Galileo, there's Sir Isaac Newton. And Sir Isaac Newton did a lot of important things in physics. Newton's laws of motion, first, second, third law of motion, are the cornerstones of all of physics and all of dynamics. But the thing that's a big deal in astronomy, besides those big laws, is gravity. Newton's universal law of gravity. And it was the very first scientific law that connected heaven and earth. He was the first person who actually came up with a mathematical relationship that explained why the moon stayed in orbit around the Earth, or why the Earth orbited the sun. For the 1700s, ladies and gentlemen, it was a wild and crazy idea, and that is why Newton and Galileo are still a big deal today, because they had revolutionary ideas. Then we're going to transition for the latter half of the chapter, and we're going to talk about telescopes. Telescopes are the tools astronomers use, and when we say Keck, Subaru, these are Hubble or James Webb or Arecibo, which collapsed recently. We are talking about some of these really important telescopes in the world, and they are the rock stars of astronomy. But we're going to talk about reflecting telescopes and refracting telescopes. How actually do they image? What's the difference between a radio telescope and an optical telescope? How do they actually produce an image? So that's what we're up to. And then we're going to talk about something called adaptive optics, which is cool. And it's how they can control mirrors with computers to actually make images taken from the ground that are not as good as space-based telescopes, but pretty darn fabulous. So let's talk about this week's lab, and this week's lab is all about Kepler's laws. We finished up last time talking about Kepler, but this week I want you in lab to spend a lot of time with Kepler's law. Kepler's 3 laws of motion, a big deal. Kepler's laws, huge monster deal in astronomy, and I want you to spend a lot of time working with these. So you're going to write out Kepler's laws. And then the first thing, Kepler's first law of elliptical orbits, I want you to draw ellipses. Now, every lab is worth 20 points. And you're going to draw 2 ellipses on the same piece of paper, turn this in, and it's going to be worth 9 points out of that 20. So actually the physical drawing of the ellipses is about half that lab grade. I'm going to point that out to you so that you draw the ellipses. I want you to have that physical experience. You're going to need paper, you're going to need a ruler, you're going to need some string. And I took a lot of pictures as I did this so that you can hopefully understand how to do this. You've got to have a couple sewing pins will work. If you got tacks, that'll work really well. And you have to get something that the tacks will stick into. I use a piece of cardboard. If all else fails, use a side of a cereal box or the side of a shoe box or the side of a, I don't know, tag board, whatever you got floating around your house. But you got to stick those in something so that the string, and you can use a shoelace, unlace one of your shoes. It won't kill you. And then use that string to draw your ellipses. Once you've drawn your ellipses, I want you to measure some things, and then I show you exactly what to measure, so it's not going to be that complicated. Then you're going to calculate the eccentricity of these two ellipses that I'm asking you to draw. The eccentricity, if you recall, is the one number. It's the one number that illustrates the elongatedness of an ellipse. A very round orbit is going to have an eccentricity closer to 0. A very elongated ellipse is going to have an eccentricity closer to 1. So you're going to calculate those numbers for your ellipses that you draw. Then you are going to calculate the eccentricities of the planets in our solar system. Easy, simple, there's the equation, simple division. You can do that with a calculator on your phone. Then you're going to go to the planetary orbit simulator using our class action app that we've used every lab up until now. I'm just going to stop. I'm to the point where I'm going to stop every lab going through, this is how you open your lab, because we've done it for multiple weeks. I hope you got it by now. So go to that planetary orbit simulator, and again, I'm going to ask you to follow the little yellow brick road, and I tell you what to click on, click off, and sketch the simulation of Mercury, Earth, and Saturn's orbits. Now, why did I pick Mercury, Earth, and Saturn? They have very different eccentricities. So I want you to see some of the most round to most elliptical orbits in our solar system. Answer some questions about this. Then we're going to talk about Kepler's second law. Kepler's second law is that law of equal areas. I want you to write that out from your notes. Then I want you to see that, click on the simulation, make that law of equal areas pop up in the boxes, and then I'm going to ask you to draw that in the same data box that you used, the same data box above, meaning this one. You're going to sketch in the pie-shaped wedges. So please sketch in the pie-shaped wedges. You're going to be drawn a little bit. It's not going to be that complicated. So sketch those in there. Then I want you to, using the simulator, follow the little instructions here. I want you to turn things on so that you create a really elongated ellipse. I tried to tweak the simulation to give you a really elongated ellipse. Comets have very elongated orbits. They come near the sun and they go really fast, and then they go way out past the outer solar system. They go really, really, really slow, and then they go and they orbit next to that sun really fast. I want you to see that with this simulation. So you're going to, in this software, you're going to make a comet in the simulation. I want to sketch what you see, answer a couple of questions about it, and that's it. I think it's not a terribly complicated lab this week. You got to draw something. You get to play with tape and string. I like tape and string. I can handle tape and string. A little bit of work with the simulation, and it's mostly drawing. And you got to divide a couple numbers with your phone. You can handle that. I totally believe in you. All right, have a good week, and we'll talk next time. Bye-bye.